Hello, everybody. I hope you guys are doing okay. Of course, the first thing you want to get done this week is your test for statistics, and that would be the priority for you to do. Once you're done with that, you'll want to come back and work with this video and look through what we're doing for this coming week. We are looking at Chapter 9 in your book now. I actually did a brief introduction to that on a different video that dealt with scatter plots. And we're going to go through this particular PowerPoint a little bit differently than what we usually do. On Canvas, you will find a couple of different handouts, one of which it's called New Coral Handout. It's a handout about correlations. And you might want to either print that out if you have the capability of doing that, or open it in another tab, or download the PDF and have it available on your phone, because there are several places in this particular PowerPoint where I'm going to suggest that you pause, work out some of those problems, and then we'll go back and take a look at them together. So the topic of Chapter 9 is correlations. And I pointed out in the previous video that a correlation is just a relationship between two variables. Technically, what you're seeing is that as one thing goes up, the other changes in a predictable way. You can see if one thing goes up, does the other one mostly go up, or does the other one go down? There are two main types of correlations that we typically look at. They're called positive and negative correlations. In a positive correlation, when one thing goes up, so does the other one. You have a scatter plot that would look something like what you're looking at here, where you can see an upward trend as you go from one place to another. One example of a positive correlation would be the cost of using a computer printer and how many pages you print. The more pages you print out, the more it's going to cost to use that printer. Another positive correlation would be the number of free throws a basketball player makes and the number of times that that person is fouled. I've had people point out before that if you're fouling at the end of a game, you're supposed to foul the guy that can't shoot free throws well, and that's certainly true. But if you're not fouled, you're not going to have any chances, and the more chances you have, the more times you're eventually going to make a shot. So yeah, as the fouls go up, the number of free throws is going to go up too. A couple of other positive correlations, the time that's required for a reading assignment and the number of pages that are assigned. If you're assigned lots of stuff, it's going to take you longer to do it. And the last one here, children's ages and the number of words in their vocabulary. The older a baby gets, the more words they're going to end up being able to say. We also have negative correlations, and the idea of a negative correlation is things are going in opposite directions. When one thing increases, the other one's going to decrease. If you had a scatter plot like we were looking at in the other video, the general trend is downward as you go from left to right. A negative correlation that a lot of people here in Iowa can relate to is how many acres you plant to corn and how many acres you plant to beans. Typically, when one crop has more acres planted to it, the other one has less. And so, this year, if prices for corn tend to be really low, you might see more acres that are planted in beans. Here's some other negative correlations. The power in a microwave and the time it takes to heat up a cup of water. If you have a very high power microwave, it will tend to heat things up more quickly than if you have a cheap microwave that doesn't have much power. And another one here, the number of checkouts that are open and how long it takes you to check out at Walmart. If you've got lots of checkouts available, you're going to get through quicker than if there's only one or two checkouts open. One more negative correlation, the number of raffle tickets that are sold and the probability for winning a raffle. If there's not very many tickets, your chances of winning go up. It is always perfectly possible to have no correlation as well. The first one I have on here as an example of that is college students' height and their grade point averages. One year when I was teaching this class, I had a couple of twins that were very tall, and they tried to tell me that there should be a positive correlation between height and grade point because they thought taller people should do better than shorter people, but really there's not any relationship there at all. Another one I have is the outside temperature and the number of problems that are assigned in class. There's really no relationship between that, and you certainly would hope that as it gets warmer outside, you're not going to have more problems assigned. So those are things with no correlation. If you go to that handout I was talking about, you'll see a section that starts off with types of correlations. And I want you to take just a minute now and see if you can go through those problems and see what type of correlation each one is. This would be a good place to pause the video and take a look at those problems. I'm going to go through these, and it does turn out some of these are much easier than others. One of the hardest ones on this section is the very first problem, where it says the grades people got on test 1 and the grades they got on test 2 in stats class. The right answer for that is a positive correlation. And what that means is that the better you did on the first test, the better you probably did on the second test. The people that did well the first time also tended to do well the second time. The people that struggled a little bit on the first test also tended to have the lower scores on the second test. Now, that's by no means a perfect correlation. There certainly are people that did well on one and not as well on the others, but the general trend was high on one, went with high on the second, lower on one tended to go with lower on the second. The rest of these are much more straightforward. Number 2, how much homes cost and the size in square feet, that one is definitely a positive correlation. If you pay more for a home, you're going to get bigger homes. The third one, the outside temperature and sales of hot chocolate at a restaurant, we had a very similar problem on those examples last time. It was about coffee instead of hot chocolate, but the idea there is that as the temperature goes up, hot chocolate sales will go down, and that makes it a negative correlation. Number 4 is also a negative correlation because if you have a more powerful car engine, your gas mileage is probably going to go down. That's a negative correlation. Last one, how many times people shower per week in the magazines they subscribe to. I think the best answer for that is 0. There's really no relationship at all. Continue over on the next page, number 6, it talks about the number of streetlights in a neighborhood and the number of crimes committed in that neighborhood at night. Years and years ago, when I was a student at UNI, I was part of the student government there, and one of the things that I am proudest of that we did is we were able to increase lighting on the UNI campus, and we did that by showing exactly this relationship that if you have more streetlights, there's fewer crimes. We actually got the lighting increased after there had been a number of rapes on campus at UNI, and it did turn out that after increasing the lighting, those went down. That's a negative correlation because as one thing goes up, the other one goes down. How tall people are and how much they weigh was another of the examples that came up in the graphs we looked at last week. That one's definitely a positive correlation, not a perfect one, but as one thing goes up, the other one goes up too. Person's income and how likely they are to be audited by the IRS, people aren't always entirely sure of. In the real world, though, that is a very strong positive correlation. Wealthy people are much more likely to be audited than poorer people. And there's a lot of good reasons for that. Wealthier people, they have more money that the IRS can take if they find something wrong. And what's more, they also have way more complicated taxes, so they're much more likely to have problems with their taxes just because there's more things that can go wrong. Number 9 is a problem that years ago I actually put on a test, and I ended up regretting it because I had people that could justify pretty much every one of these possible answers. It says the balance in a person's checking account and how far that person drives to work. And when I originally wrote that question, my intention was for the answer to be zero, that there just really isn't a whole lot of relationship at all. But I had people that very legitimately argued for positive and negative. The people that said positive, what they were looking at is very often the reason why people drive a long ways to work is because they can get a better job by driving a long distance. I live in Algona, and there's people here that work in places like Forest City and Mason City and Fort Dodge, and they'll drive an hour to work because they can make a lot more money by driving that distance. That would be a positive correlation if you said it that way. Some people said negative correlation, and their reasoning was that if you spend all your money on gas, you're not going to have a lot of money left in your checking account. That was also a reasonable answer to come up with, and in the end, when I did put that on the test, I threw out the question. And all of those could actually be pretty logical, but the fact that you could justify both positive and negative kind of makes zero a better answer anyway. So yeah, that I did intend it to be zero, but I accepted all the possible answers on that. The last one on this section, it says how much a store charges for a product and how much of that product they sell in a day. That's a perfect idea of economics, and what it is a negative correlation. When prices go up, people tend to buy less. When prices go down, they tend to buy more. You can think about, if you think back 3 or 4 years when gas cost a lot more than it does now, people were looking at how much they drive and they tried to limit their driving as much as possible. At the moment, gas is as cheap as it's been since back when I was in college. And while there's not really a whole lot of places to drive while you're under quarantine, if you could, it wouldn't cost you much, and so you wouldn't really care about how much you were spending on gas. In general, when things go up, people tend to buy less. When things go down for the price, they tend to buy more. That's a negative correlation. Back to the main explanation. The next key thing that comes up is the fact that just because there's a correlation between things, it does not mean that the first one causes the second. And that really is kind of important. You'll often hear studies reported on TV or see people on the internet that are saying one thing causes another. And it's all but impossible to show with statistics that there's a cause and effect between anything. You can show that there's a relationship, but you can't say one thing causes another. Again, we just can show that there's a relationship. When one thing goes up, the other one tends to go up or down as well. But there could be something else that's affecting both of those things we're studying. In statistics, we call that a lurking or confounding or extraneous variables. Those three words basically just all mean the same thing, and they mean there's something in the background that's really what's doing the causing of what we're noticing. A real classic example that comes up almost every time people talk about statistics is the fact that it's been shown that there's a strong correlation between children's shoe size and their vocabulary. Which sounds like having bigger shoes must cause kids to know more. So you should put all your kids in like clown shoes and that would be a good thing. But big feet isn't what's causing kids to have a bigger vocabulary. What's really going on is you've got another variable, which is age, that affects both of those. As kids get older, they wear bigger shoes and they also know more words. And because of that, that lurking variable here is going to be age. Here's an example that comes straight out of your book. It says, over the past 30 years in the United States, there's been a strong negative correlation between the number of infant deaths at birth and the number of people over age 65. Is it a fact that people living longer is causing a decrease in infant mortalities? Well, no. And then they go into the second part, what lurking variables might be causing the increase in one or both of those variables. Well, the idea here is that we have better medicine in general. And what that's doing is it's causing people to live longer, and it's also causing fewer babies to die. And so, as our science, as our medicine improves, you have changes in both of those things, but the fact that there's more old people doesn't mean that there's going to be fewer babies dying. I actually noticed in the last video that you can show correlations using what we call a scatter plot. And all that is just literally a graph that's showing you where each of the points that you would have is. I could look at like a kid's shoe size and how many words they know, and the X is their shoe size, the Y is how many words they know, and I just plot those on a graph. I already mentioned, but I'll sum it up again, that a positive correlation would mean the trend of those points is basically upward as you go from left to right. In a negative correlation, it's mostly going downward. I also talked last time about the difference between a strong and a weak correlation. A strong correlation, your dots would be packed very closely together, almost in a straight line. In a weak correlation, they're spread out all over the place. If you had a perfect correlation, all those dots would literally be lined up in a straight line. And if there was no correlation at all, they would be all over the place with no pattern to where they were. Now in this class, what we're looking at is what we call linear correlations. And that means we're looking at patterns that are close to being in a straight line. It is very possible in the real world to have patterns that aren't really in line. You're looking at the picture, for instance, of what we call a sine wave. This comes up in any sort of pattern that might be cyclical. Like, for instance, you could look at the temperature outside. It tends to be warmer in summer, cooler in winter, warmer the next summer, cooler the next winter. Or you could even go through and think hotter during the day, colder at night, hotter the next day, colder the next night. When things go up and down, that's a pattern, but it's not a line. There are a lot of patterns that are not lines, and if you went on and took a different statistics class, you might look at the math of how to do that. From our point of view in here, though, if you see a pattern that's not a line, we would say that there's no correlation, or no linear correlation. How strong a correlation is can be measured using a statistic called R. R is the correlation coefficient, and it will always end up being a number that's somewhere between -1 and 1. If you have a negative correlation, you're going to get a negative value for R. If you have a positive correlation, you'll get a positive value, and it will always be somewhere between -1 and 1. If R was 0, we would say that there is literally no correlation. If R is 1, or if R is -1, you'd have a perfect correlation. A perfect positive correlation, R would be 1, have a straight line where everything's going up from left to right. If you had R equals -1, you'd have a straight line going down from left to right, and it would be a perfect negative correlation. Most of the time, though, R isn't 0, and it's not 1 or -1. What it's going to be is a fraction or a decimal that's somewhere in the middle. There's no magic rule on how to interpret how strong a correlation is, but a lot of times what we'll say is if you have a fraction that's bigger than a half or bigger than 0.5, we'd call that a strong correlation. And turning that around, if it was less than a half or less than 0.5, it's going to be a weak correlation. Now again, there's nothing magic about those numbers. Sometimes I've seen books where they will divide things up into thirds and they'll talk about weak, medium, and strong. And that's perfectly okay as well. But the idea is the closer you get to 1, the stronger the correlation is. The closer you get to 0, the weaker it is. If you have negative correlations, it's close to 0 and close to -1. This picture was actually in the video last week as well, but it's showing you just a wide range of scatter plots. And if you look carefully above it, you'll notice that they have the value of R written in here. They do have things like on the first one, it's -1 because all those dots would be in a perfect straight line. You have negative correlations at the top, but they get more and more spread out as the value of R gets smaller. And then they go through 0 and various positive numbers until we get positive 1. So again, I'm going to suggest that you pause things for a minute next. The next part on this, it's asking you to talk about the strength of a correlation and then to also come up with a value for R. And I want you to just see if you can think what those might be, and then we'll talk about what would be a good idea for those values in just a second. Well, here's those problems, and I can look at number 11 and tell right off that it's a negative correlation. And it's actually a fairly strong negative correlation. Now, there's no hard and fast answer of what would be the value for R. If I were doing it myself, though, I would probably say something like negative 0.8 or negative 0.9. It's a pretty big negative number, and again, the biggest you could have would be negative 1. Number 12 is a perfect positive correlation, and that would be 1. Number 13, when I look at that, I don't really see any pattern at all, so I would probably put 0 and say that there's no correlation. Number 14, it's a positive correlation and not a terribly strong one. Now, I will tell you, if you can see the pattern, it's going to be closer to a half than it is to 0. And in reality, this might be 0.4 or 0.5. It might even be 0.6, actually. But it's way less of a correlation than what we had on number 11, and that's why it would never be anything close to like 0.8 or 0.9. Again, somewhere around 0.5 is probably a pretty good answer for that one. 15, half of this goes down, half of it goes up, and that's why the answer is going to be that there really is not any linear correlation. I just say no correlation. And if I were to put an R value, it would be 0. Basically, the left side is negative, the right side's positive, and they cancel each other out. And on number 16, it's a negative correlation. It would actually be a stronger correlation than what you have on number 14, but not nearly as strong as what's up on number 11. And that's why I'd probably say something like 0.7. It would be negative 0.7, actually, if I had to pick a number for this one. There are a couple of other questions that came up on the worksheet right after those patterns of dots, and I'm just going to go through those real quickly. The first one says, how would you report the findings of a study that had a linear correlation of negative 1.34? Well, I would say somebody screwed up, because that's impossible. The R value has to be between negative 1 and 1, and this is less than negative 1, so it can't happen. The second one says, well, what if you got a linear correlation of positive 0.3? I would say it's a pretty weak positive correlation. It is a positive correlation, but it's not really all that strong. There's a relationship, but there's probably more difference than there is a good relationship between your variables. And the last one there says, explain how you could have a correlation coefficient of 0 when the data shows a definite pattern. Well, this is one of those where you've got a pattern, but it's not a line. And you might have something like that sine wave I used as an example earlier, or it could be like number 15, where we have what's called a parabola, where it both goes down and up in the same picture. Either of those would be a good example of something where it would be 0, but you do have a definite pattern. There is actually another way that you could get that, and that's if you had either a horizontal or vertical line. Either of those would also end up having a correlation coefficient of 0. So next up, we're going to talk about how to find R on your calculator. And the first thing that we need to talk about is something that you've got to do, but it always seems kind of weird to do it. You want to, before you do anything else, go to your calculator and hit second and the 0 key. This will even be true if you downloaded a calculator to your computer or phone. You've got to basically tell the calculator that you want to be able to find R. So you hit second 0 and you get into what's called the catalog. And what you're going to do is scroll through all of this big long list of all the different things your calculator can do until you get to a choice that says Diagnostic On. You scroll all the way down to the D's, find Diagnostic On, and then you're going to hit Enter when you get there. Actually hit Enter twice. All it does on your screen is it says Done, and it doesn't look like you did squat, but if you don't do that, your calculator is never going to tell you what R is. And so that really is important. Go to second 0, scroll down to Diagnostic On, and hit Enter twice. Once you've done that once, that'll be stuck in your calculator forever and you don't need to go back and worry about it changing, but you do have to do that once before you do any of the problems we're going to look at. So then, once you've done that, you're going to actually next go to Stat Edit to your lists like we've done before. And what's going to happen is you'll have pairs of data. I'll show you an example of that here in a second. You want to put the first variable in list 1 and the second variable in list 2. And of course, we talked about putting variables in lists clear back at the beginning of the semester. It is important that you pair up the things so that they're together. This is actually the next problem in that worksheet I've been going through. And you can see that what I did is I went to Stat Edit. And in list 1, I put all the numbers of children that these families had. Like you can see the last few of those, I had 4, 2, and 3 children. Basically, I'm copying the list, but I'm going down instead of across. List 2, I put the number of doctor visits that each family had. Like the last 3 numbers there are 10, 2, and 9. And again, I just put the entire list of children, the entire list of doctor visits, and I've got to be careful to make sure that I do keep things paired up. Like that family at the end with 3 children had 9 doctor visits. So I put all of those in there, make sure that both lists are done. Once you've got all the numbers in both lists, you quit out of there. You hit second and the mode key, which is right next to second. And then you go to Stat Calc. Now, where you go is not necessarily where you're going to expect. You choose the choice that says Lin Reg. It's choice 4, and it stands for linear regression. We'll talk about what that means in a little bit. But you want to make sure you go down to choice 4, hit Lin Reg, and then hit Enter until you get some answers. And what's going to end up happening is you'll get a readout that looks like what I have down at the bottom of the screen. Now, if you didn't do that first step I said about putting Diagnostic On in your calculator, it's not going to have the R squared and R at the bottom. And you need to go back and make it calculate things by choosing Diagnostic On. What we care about, though, is down at the bottom of that screen where it says R equals 0.8198. That's the value of R that goes with this problem. And so when it says calculate a value of R, okay, it's like 0.82 would be what I'd probably write down. And we're saying that there's a pretty strong positive correlation between how many kids a family has and how many times they go to the doctor. And just like you can with T and Z, you can do significance tests for correlation, for R. What you're trying to do is figure out whether you have a significant positive or negative correlation. Is it strong enough that it didn't just happen by chance? Now, I'll be honest and say this is just about the least important topic in this chapter, but it is something that we're going to go through, and part of the reason I do make a point of including this is that it shows you a different way that you can do hypothesis tests. When we deal with R, we're not going to find the p-value. We're going to do what's called a classical hypothesis test, where we compare the R we compute with a table. And that's exactly why there's a table that's on the front page of that handout that you were given. What you do is you're going to use that handout to look up a value of R. It's what we call a critical value. The way you do that is you'll find N, which is the number of things that were in your sample. Another way to think about it is the number of pairs of data. The number of points you'd have if you plotted the scatter plot on this. That's what your N is, and you'll put that together with alpha, and it's going to tell you a critical value. It's like a cutoff line that tells you whether R is big enough or not. You can always compute R exactly like we just talked about, where you put your two lists in the calculator and then go to linear regression. There are a lot of times, though, that number is given to you, and what you're actually asked to do is compare that and make a decision. The way that we figure out whether we have a significant result or not is that you want the calculated value to be bigger than the number that's in the table. When you do that, you always compare the absolute value, so if there was a minus on your calculator, you just get rid of it. But if that number is bigger than the table, then you have a significant result. If it's smaller, you don't. And that is sort of the opposite of what we did with p-value. You wanted the p-value to be small. For an R test, you want that number to be as big as it can possibly be, bigger than the cutoff line that's in the table. With that in mind, I want you to look at the next part that comes up in that handout and see if you can figure out what the R numbers are and then figure out whether or not you do have significant results. So here is problem 21. Again, if I want to calculate R, what I've got to do is go to Stat Edit. I put the anger hostility scores in list 1 and those depression dejection scores in list 2. You then go to Stat Calc and go down to linear regression, and here we found that the R is 0.665. What I've got to do now is compare 0.665 to the table, and the way I do that is I look up how many pairs of data I have. There are 8 pairs of data, 8 subjects they looked at, and what we want to do then is to go to that table. It says the 5% level of significance, so if I go to 8 and 0.05, the critical value is 0.71. I compare my calculator with 0.71. This time 0.665 is less than that cutoff line, and that's why in this case, no, there is not a significant correlation. There is a relationship, but it's not strong enough that I can say it didn't just happen by chance. You do pretty much the same thing on number 22. Here I calculated that the R value was about 0.72. This time we have 12 cities, and I go to the 0.01 level of significance. The cutoff line this time is 0.71, and now my calculator is just a little bit more than that, so yes, this would be a significant result. Again, whenever you're doing an R test, you want the calculator to be bigger than the table. If the calculator is larger, then yes, it's significant. If the calculator is less, no, it is not. The next topic that comes up in this chapter is what's called the coefficient of determination. Coefficient of determination is R squared, and you probably noticed a line on the calculator readouts that said R squared. That's literally the number R taken times itself, R squared. And what that does is it tells you the amount of change in the second variable that you could predict from the change in the first one. So if I thought back about that relationship between how many kids a family has and the number of doctor visits they make, this would be the amount of the difference in doctor visits that has to do with how many kids there are in a family. How much of the second one you can predict from the first one. This literally is R squared. For example, if R came out to be 0.7, you'd square that, you get 49%. 0.49, and you could say that 49% of the change in y was due to the change in x. There's like a whole page in that worksheet that deals with correlation and determination. And again, this will be a place where you might want to pause the video. You're going to be finding r squared and then answering some other questions related to that. So this first one, it's asking about people's age and their willingness to give out credit card information over the internet. And it tells you that they had a value of negative 0.68 for R. And the first question says, what percentage of a person's willingness to give out their credit card information could be attributed to their age? Well, that attributed to is exactly what R squared is, and that's why what I'm going to do here is take negative 0.68 squared. If you do that, we're going to get about 46%, 0.4624. The second question says what percentage would be due to other things besides age? Well, if 46% is because of age, then 54% would be because of other stuff. I can always just subtract from 1 or subtract from 100% to get that idea of other factors. And the third one, it says, explain what the negative correlation in this problem means. As older and older people were sampled, what happens to the ratings? Well, remember, a negative correlation says when one thing goes up, the other one goes down. So here we'd be saying as people got older, they were less willing to give out their credit card information. And that would be what our survey is about. Basically the same kind of thing on the next one where they're looking at how long employees have been with the company and what their level of job satisfaction is. For part A, I took the R value that was given and I squared it, and it's like 0.765625 or about 77%. The amount of job satisfaction that's due to other things, I subtracted from 1 and got about 23%. And since it's a positive correlation on part C, we could say the longer people have been with the company, the better they feel about their job, basically. The long-time employees are going to have more positive ratings than the new ones. Problem 25 is almost the exact opposite of the previous two problems. This time they're referring to a real study that was done back in 1952 in California where they had people drink more and more, and they didn't have them drive, they had them do different tests to see how alert they were. And they did find out that 50% of the variation in alertness could be attributed to how much people drank. Well, what we're supposed to do is find R. Well, they're giving us R squared. They're telling us the amount of change in alertness that's due to how much you drank. So I know R squared is 50% or 0.5. The way you find R then is you do the square root of that. And it turns out you get about 0.707 for what R would end up being. The other question that's here is to explain what the negative correlation means in this problem. Well, negative, again, means when one thing goes up, the other one goes down. And if you've either drunk anything yourself or you've been familiar with people that have, you know that the more people drink, the less alert they are. That's why this is a negative correlation. And the next couple questions kind of tie together all the different stuff we've talked about. We have this one that talks about the artificial sweetener saccharin. You can still find saccharin in pink packets in restaurants, but not a lot of people use it to sweeten other things today. We've moved on to things like aspartame and stevia and various things like that. But it used to be, back when I was a kid, that saccharin was what Diet Pop and Diet Anything was made with. Here they tell us that 25% of the variation in one thing is due to another, and again we're supposed to find R, so what I did is I took the square root of 0.25, and part A is going to be 0.5. Then they ask you a question about whether this was significant. It says the study involved 24 rats, find a critical value, and it says at the 0.01 level of significance. Well, if you go to the table and you look up 24, you'll notice that the cutoff line that goes with 0.01 is R would be 0.52. The calculated number we got was 0.5. That's a little bit less than 0.52, and that's why no, this was not a significant result. So, yeah, the critical value is 0.52 on part B, and part C, no, it is not significant. How would you describe the correlation? Well, since it's 0.5, that's about as middle as you can get. I'd probably say it's a moderate or medium positive correlation. It actually was reported back in the 70s that saccharin caused cancer, and it says, according to this study, is that a correct conclusion? Well, the answer is no for a couple of reasons. One of them is that they didn't get a significant result. But really more important with that is even if they had, you can't say one thing causes another. There could have been other things going on in the background, and that's why it's definitely not cause that you can say. If you ever see that word cause, like on a quiz or a test, the answer is no. And part F is just sort of a think about it question. It is interesting that lots of different places in the world did ban saccharin, but you actually still can get those pink packets all over America. And sometimes people wonder whether that should be the case. We have replaced it with things like NutraSweet or aspartame. That's actually a sweetener that's been banned in some places too. You can't get NutraSweet in Mexico, for instance. But usually in this country, what we try to do is give people information and have them make decisions, and that's largely what was done with saccharin. On number 27, they tell you in the problem that R is 0.43. And it says use a table to find a critical value at 0.05, and if you do, look at the fact that we had 20 NBA players. For the 5% level of significance, your critical value would be 0.44. 0.43 is less than that. It's a little bit less, but it is less, and so that's why it would be no for part B. Part C is going to be 0.56, and we're definitely less than that, so it's still no on part D. And on part E, it says what percentage of the variation in how many points pro basketball players score is due to the difference in height. Well, what they're asking you about is that coefficient of variation, and that's why I took 0.43 squared, and it ends up being about 18.5%, 0.1849. So there's a lot more of the variation in points that's due to other things besides height, things like, well, people's skill, for example, as opposed to just how tall they are. The last problem in this section, it talks about the fact that 49% of the variation in gas mileage is due to how much cars weigh. Once again, they're giving you R squared, and what you've got to do is find R, so you've got to take the square root of 0.49, and it turns out R would be 0.7. The last topic that comes up in this section is linear regression. And when you do linear regression, what you're doing is you're using a line to make predictions about what's going to happen when you have two variable data. And what you're essentially doing is sort of finding the average of that data. What's literally going on is if you picture your scatter plot with all those dots showing how when one thing changes, the other one does too. If you drew a line right down the center of where all those dots are, that's the line that is like the average that we're going to use to estimate. You're finding a line that's as close as possible to every single point in that set. You probably know from algebra class that most of the time you write lines in the form y equals mx plus b. Technically, when we talk about a regression line, we usually write it as y hat equals m times x hat plus b. That's just the equation of a line, and you might have actually noticed that when we were finding r before on the calculator, there were a couple of other things that showed up on that screen. It said a and b. All those are the slope and the y-intercept of a regression line. They're basically the m and the b that come up in this formula. Now, we're not going to actually be calculating linear regression in this class. You might encounter a different stats class later in life where you will be doing that. But in here, what's going to happen is you're going to be given regression lines and using them to make some decisions or figure out some answers. When you look at the equation for a regression line, the slope, the m or the number by x, it tells you the rate of change in one of the variables. If I thought back to, for instance, that problem about how many kids families have and how many visits they make to the hospital, what the slope would be telling me is for each additional kid that you have, how many visits does that increase your family trips to the hospital? The y-intercept, the number that's at the end of the problem, the b, what that typically is the initial value. It would be like if somebody had no kids, how many visits are they likely to make to the hospital? Again, what a regression equation really does is it looks at like the average of everything and it makes the best estimate it can based on the data that you're given. I looked at some of the terms we did in the earlier chapters. What you're really finding is a point estimate of where things would really be. But it does turn out that especially when you're using values that are far away from the ones that were used to get a sample, you can get some answers that aren't real accurate and sometimes can honestly be pretty silly. And we're going to look at least one example of how that might work. So to give you an idea of how you can use a regression equation, we're going to look at this example. It says the New York City Police noticed that as the number of officers on the street increased, the crime rate decreased. And your common sense ought to kind of tell you if you have more cops around, probably there's going to be less crime. Now, the equation I have here is totally made up. It says in a certain precinct there was a linear correlation with the regression equation y equals 135 minus 7x, where x is the number of officers and y is the number of crimes that were committed each day. So if you tell me how many cops there are in the street, I can tell you how many crimes there's likely to be. We're going to look at 3 questions related to this situation. The first one, it says how many crimes can be expected with 12 officers on the street? So I'm giving you 12 officers. We need to figure out how many crimes. What you do here is basically just plug in 12 for x and see what y is. So 135 minus 7 times 12, we end up with an answer of 51 crimes. That's all I do. Now, the next one's a little bit different question. It says how many officers would be needed to reduce the number of crimes to 20? So if you think about this for a minute, what they're doing is giving you the number of crimes, and we need to figure out how many cops would make that happen. And what you're going to do with this one is to plug in the number we have there, the 20, for y. So I know that 20 would equal 135 minus 7x. We got to figure out x, the number of officers. So you solve an algebra problem, you subtract 135 and you divide by -7, and the answer my calculator says is 16.4. Now this is a situation where you would do exactly like you did back when we were doing those sample size problems earlier. You're always going to round the answer up. The answer that I should actually say here is 17. Because if I only had 16 officers, I wouldn't reduce it quite enough to be down to 20. It would be 20 something, but it wouldn't be exactly 20. If I have 17, it's going to be more than enough. And the third question on here, it says how many crimes would be expected if there were 25 officers on the street? And I put in there that you want to notice that's a very large number of officers. It's way more than like the 16 or 17 we got in the previous problems. That's actually kind of important. This problem is actually a lot like the first one. I'm giving you how many cops, you figure out how many crimes, so you're just going to plug in for x and see what you get. But if you do plug in for x, you get kind of a weird answer. If you take 135 minus 7 times 25, you get -40. So we have a negative number of crimes. You know, all the robbers are, taking the jewels back to the jewelry store and taking the money back to the bank and all of that stuff. So, it really is an impossible answer. And the reason that happens is that 25 is a way bigger number than what would they use to come up with that equation to begin with. So you do get kind of a ridiculous answer. In the real world, since you can't have a negative number of crimes, what we'd probably say is it's essentially zero. There is a regression equation section on your worksheet, and again, we're going to give you just a minute to look through those and see what you can get. So the next problem here, they give us an equation that's supposed to figure out how much a law firm's phone bill would be based on how many long-distance calls they make. And the first two questions, they give you a couple of numbers of long-distance calls. You're supposed to figure out what the bill is. If you look at the bottom left, I did that. I just went to the formula. I plugged in 142 for X, and then I plugged in 25 for X. And the answers to A and B would be $306.41 and then $98.15. So those are pretty straightforward. Plug them in and see what you get. Part C, we have this really stupid question where it says that the firm's financial advisor suggests they limit their phone expenses to no more than $150 a month. Now, if my lawyer cares about how much they spend on the phone, I think it's probably time to change lawyers because they certainly ought to have enough money to pay a phone bill. But since that's what it says, we'll do what the problem's telling us. They're giving me the y. They're giving me that 150 equals 5365 plus 178x. And what I've got to do is subtract and divide. The calculator's answer here is 54.12, which, since I can only make a whole number of phone calls, means they can only make 54 calls. The other two questions are asking you what the numbers in the equation stand for, and I do have a typo in part D. It should say 5365. What that would be is like the base bill. It's what they pay to have a phone in the office even if they never use it. If they make no calls at all, they've still got to pay $53.65 to the phone company. The 178 would be how much they pay for each long-distance call that they make. Now, there's really no plans I'm aware of anywhere that charge a flat rate per phone call, but that might be like the average cost for each long-distance call. That's a possibility. At any rate, it is like as each call they make, they're going to be spending $1.78 more. And the other problem here, it says to be careful of units of measurement. And what they're telling us is what's going to be the resale price of a car that is a certain number of years old. And the first one is what would you have for a 3-year-old car, then what would you have for a 6-year-old car? Well, what I did here is I plugged into the formula the numbers for X, and you notice the answers I got were 161.14 and 96.58, which if you look at this quickly, you could almost think that that means I could buy a 3-year-old car for $161.14, which isn't very likely. What's really going on here is if you look carefully at the problem, it tells you that Y is in hundreds of dollars. And that's why what I did right below that is I took those answers times 100. And technically the first answer would be 16,114 and the second one is 9,658. Both of those are actually impossibly accurate answers. In the real world, you'd say about 16,000 and probably about 9,600 would be what we'd end up saying for those prices. The third question says, when will the car be worthless? Well, worthless would mean it's worth $0. So what you can do is plug in 0 for Y. And if you do end up solving that, here I actually divided by a positive number, which is why my answer technically shows a negative. But what you would end up getting is about 10.5 years. That's actually, in the financial world, a lot of times 10 years is used for the amount you're allowed to use for depreciation on expenses like a car. And so, yeah, 10 and a half years, you would have basically a worthless car. And the last one says, what's the annual decrease in the resale cost? Sometimes I'll have people that will like take it between 0 and 10, plug all of those numbers in, and then find the average of them. And boy, is that a pain. The answer is $2,152. Basically, it's the slope. It's the number that's by x. What the equation is telling us is that this car initially cost $22,570, and each year it goes down by an average of $2,152. So again, the slope is how much it changes per year. The y-intercept is what the initial value of it was. So we covered a lot of ground there, but hopefully that does go through most of what you want to know about correlation. In Canvas, there's two different documents that you can use to get a little bit more practice with these. One of them is you still have a couple more pages of that worksheet that you've been going through that say review. And I would suggest that you look through those and you figure out what the answers are to things. The answers are also going to be posted there. There's also a handout that says correlation review with answers. And again, it's just another worksheet that gives you practice with all the different kinds of problems that we've gone through. So I would suggest that you practice with all of those. And then next week, you will have a quiz coming up that is about correlation. So that's what's new this week. Hopefully your test went fairly decent. Have a good week, and we will talk to you again later.